We saw earlier that H3O plus increases the solubility of a slightly soluble ionic compound if its anion is that of a weak acid, or simply its conjugate base. Likewise, a ligand increases the solubility of a slightly soluble ionic compound if it forms a complex ion, but this time with the compound's cation. To see the effects of complex ion formation on solubility, we couple or add the dissolution equation with its KSP value with the formation equation and its KF value, just like we see here. Once we couple them together, we make sure to get rid of any species that is the same on both sides of the equation. We then multiply their equilibrium constants to get an overall K value. We can use this overall K value to get the molar solubility with the new equation created from a Rice table. For example, iron 2 sulfide is a slightly soluble ionic compound, okay? And for us, we'll call it FeS Wolverine. Why? Because Wolverine has the ability to regenerate. So I always think of something that's going to be saturated or something that's going to have solubility attached as having the ability to regenerate that solid once they are at that equilibrium. So we have FeS solid in equilibrium to form Fe2 plus S2 minus. The KSP value for this overall dissolution is 8 times 10 to the negative 16. When we add 1.0 molar, for example, of NaCN, so the Na plus ion doesn't react, but the Cn minus ion acts as a ligand and reacts with a small amount of the Fe2 plus. And guess what? They form the complex ion FeCN6 4 minus. And the formation of this complex ion has a Kf value of 3 times 10 raised to a power of 35. Since we already have our KSP and dissolution equation, and we already have our Kf and our formation reaction, we can couple or add these overall reactions together. So when I add them together, what you want to do is get rid of species that are the same on both sides. That means we can get rid of Fe2 plus and Fe2 plus. And you want to bring down anything that's left over. So we have FeS solid left over, we have the 6Cn minus left over, and we have our S2 minus left over, and we also have our complex ion that was formed that's going to be left over. Since we added these two reactions together, again, what's left over is going to now have a new K overall, or a new equilibrium constant. So what do? We take our KSP value and we multiply it by our KF value. That means we're going to take our 8 times 10 to the negative 16 and multiply it by 3 times 10 to the 35, and it's going to equal 2 times 10 to the 20. What does that actually mean, though? It means that since some of this Fe2 plus was taken out of reaction, right? What's going to happen to the equilibrium? The equilibrium is going to shift to the right to form more of that Fe2 plus. So the overall dissociation of FeS into ions has increased. How much has it increased? 2 times 10 to the 20 of an increase. So that is a lot from our KSP value that we started with. That goes to show you that the presence of a ligand, has a huge influence, right? Now I'll tell you straight up, when you're doing the homework or even when you're on the practice exam or the real exam, a lot of times you're not going to be given these overall reactions. So you have to make sure you do a couple of steps. One, you need to get the KSP expression, and of course you need to come up with the dissolution equation on your own. Another thing is you need to get the KF expression, and you also need to come up with the formation reaction on your own, just by what's given in the question. And then, of course, go through the steps of combining them, getting rid of the same species, of course, and then getting the K overall by multiplying the KSP by the KF value. Once you have this, you're going to take this new equation here, and you can go ahead and solve for the molar solubility, for example, which would be this, or whatever S value, or whatever is going to be our X value in our Rice table. And again, you can use the Rice table to solve for whatever you want in equilibrium. So it's just going to be the same as anything else at that point. And sometimes you won't hear it be talked about like in the textbook, for example, and separated as complex ions and solubility like I do it. But just know that it's also called coupled equilibria. And so sometimes you'll just see that. It means the exact same thing, folks. The process is also the same. So you will see coupled equilibria, or you'll just see it separated as complex ions and solubility. Or you just ask yourself, okay, what's going to be the effect of complex ion formation on solubility? And you would always have to think, well, I need to merge together or couple together or add together KSP, dissolution equation, and a KF formation equation. You can also have complex ions of amphoteric hydroxides. So amphoteric because it acts as an acid or a base, and hydroxide because it contains OH. Many metals that create amphoteric hydroxides, like aluminum hydroxide, are only slightly soluble in water. So as we see here, we have aluminum hydroxide, and we have aluminum hydroxide here. In water, you see a lot of the precipitate. Just like we see here, we see a lot of the precipitate that's going to form. But when you take that same aluminum hydroxide and you mix it in a more acidic solution or a more basic solution, guess what? It becomes more soluble, just like you see here in acidic solution and here in basic solution. With H3O plus or an acidic solution, it's going to end up reacting with OH. When it reacts with OH, it's going to decrease the OH concentration and it's going to force equilibrium to the right. And so it's going to continue to produce more and more soluble ions, which is what we see here. For the basic solution, you're going to have your AlOH3 or your solid mixed with OH minus. And so they're going to end up forming water and then also forming a complex ion here. So this complex ion, AlOH4 minus, is going to continually be formed as the OH minus is added. And so again, the formation of that complex ion just ties into everything else we've been talking about. And it, of course, connects how we can relate complex ions to solubility. Now let's head to the Avengers compound for our final example for this lecture. So it says we're going to be calculating the effect of a complex ion formation on solubility. In black and white film developing, excess AgBr is removed from the film negative with hypo, an aqueous solution of sodium thiosulfate, which causes the formation of the complex ion AgS2O3 2,3-. We are to calculate the solubility of AgBr in 1, or A, water, and then calculate the solubility of AgBr in B, 1.0 molar of this hypo or sodium thiosulfate solution. They gave us the equilibrium constant of formation for AgS2O3 2,3-, which is 4.7 times 10 to the 13. And they also gave us the KSP value for AgBr, which is 5.0 times 10 to the negative 13. Of course, we're thinking coupled equilibria, we're thinking complex ions, or our KF value, and we're thinking our KSP value. We have to make sure that we add them together. So we definitely have to get a dissolution equation for AgBr and KSP, and also get a formation equation for AgS2O3 2,3-, and of course the KF value. But before I jump the gun and couple them together, let's go ahead and just focus on AgBr and water first. So I'm going to go ahead and get my dissolution equation for AgBr, and I'm going to focus on, of course, calculating the solubility when it's completely just mixed in water. So for letter A, since we're only mixing AgBr in water, it's going to be similar to what we've done before. We're going to first get our dissolution equation. So we start off with a solid, we mix it in equilibrium to form its actual ions, right? So that's Ag plus and Br minus. We then complete a Rice table. Now, Rice table is basically going to tell us, some folks don't have to complete a Rice table. I'll tell you that straight up. Some folks will just automatically know that this is these two X values here. But again, if you want some kind of strategy for yourself, you can't just throw the Rice table in there because we are in equilibrium. So we set up our Rice table here, and then you know that solids don't matter for us because they're going to be pure solids. We're starting at 0 for our products here. They're both going to be X. So KSP is equal to Ag plus multiplied by Br minus, which is equal to X times X. That entire thing is going to equal to 5.0 times 10 to the negative 13, because that's the KSP that they gave us. This entire thing is now going to equal to X squared, which is going to now equal to 5.0 times 10 to the negative 13. I take the square root of both sides. Once I take the square root of both sides, I now can solve for X, which is going to equal to 7.1 times 10 to the negative 2 molar as my final answer. Why is it my final answer? Because they wanted me to calculate the solubility. They're asking me to calculate the solubility. They're asking me for molar solubility here. They didn't tell me that it had to specify in any kind of particular units. So I can get away with this using molar solubility. Molar solubility, of course, is going to be based on the X value in our Rice table that we have here. Now we can move forward and erase this and go to letter B. We should make sure we specify this is letter A. We're going to move forward to go to letter B and actually get to coupling our Kf value and our KSP value. Okay, before anything, we have to once again get our dissolution equation and our formation equation. So for AgBr, we just saw before, we know it's going to go into equilibrium to produce Ag plus and Br minus. We already have our KSP value. But for the formation of this complex ion, this is where a tiny little bit of work comes in. Now for me, of course, I already remember that Ag usually is going to like to be in a +1 state, okay? That means I'm going to have 2 of my S2O3s, and I know they have a charge of 2 minus. I'm automatically just going to form my overall complex ion, and it usually works out that way. But of course, it's easy to get the Ag plus charge. We've seen this in chapter 19. So once again, I can have my Ag S2O3 2 minus equal to the charge itself. So I'm going to let Ag be X. I'm going to add it to 2 times the 2 minus charge of the thiosulfate here. This whole thing is equal to 3 minus. That means I'm going to have X minus 4 is equal to 3 minus. I'm going to add 4 to both sides. So I literally have 3, or really 4 minus 3. And so I have 4 minus 3. What's that going to leave us? +1. That's another way I got my Ag plus here. Okay, folks? I also know the charge here. So then I have this. So this is just a tiny little way you can layer chapter 19 information, or even bring it back as a throwback, right? Especially when it comes to these complex ions. Don't let yourself get overwhelmed. Always just stop and breathe and remember that some of this stuff is from previous information. Now that I have my formation formula and I have my dissolution equation, I am going to couple them together. That means add them together. So I'm going to get rid of things that are the same on both sides. For us, that's going to be Ag plus here and Ag plus here. So that's going to leave us with AgBr solid plus 2 S2O3 2 minuses in equilibrium to form a Br minus plus Ag S2O3 2 3 minus. Okay. We also can now get our K overall. Since we coupled or add these reactions together, we now have to multiply the equilibrium constants. So that means we have to multiply 5.0 times 10 to the negative 13 to 4.7 times 10 to the 13. And I get the value of 24. But that's not all, folks. They want us to calculate the solubility of AgBr. So that means we need to take our new equation here and we need to solve for the molar solubility of our equation, which is usually going to be what value? Our X value in our Rice tables, okay? So we're going to use our new K overall, and we're going to use what's given in the equation to answer these questions. So I took my new overall reaction here, AgBr solid plus 2 S2O3 2 minus, in equilibrium to form Br minus and Ag S2O3 3 minus, or S2O3 2 3 minus. Sorry, folks. And of course, I had to create my Rice table. Now, they only gave me 1.0 molar of hypo, which we know is going to be the sodium thiosulfate, which represents our thiosulfate ion here, okay? Another way you could have found that S2O3 was actually 2 minus here, which is simply by what was given here, okay? Now, again, because we have a Rice table, we know we do not have to focus on solids. And again, you don't want to confuse yourself. You want to use the new overall K value because you're using the new overall reaction. Don't get caught up and start using KSP and KF anymore. We're done with those. We've already used them before, okay? So it has to be the new K overall value. So K overall is going to be our products divided by our reactants. And so we have to go ahead and fill out our equilibrium amounts. We start off initially with 1.0 molar here, 0, 0 for our product. We start off with minus 2x because there's a 2 here, and then we have x and x. Therefore, we're going to have 1.0 molar minus 2x for equilibrium here for our thiosulfate, and then x and x as our molar solubility, which is what we're trying to solve for. Right, folks? And then just by looking at the overall K value, you should automatically be thinking quadratic equation. Now, you know you're not going to be given quadratic equation, right? Especially on like an exam or something like that. So we're looking at perfect squares, for example. All right. That means we're going to have our 24 is equal to x squared because I've just plugged in my x values here, and I've plugged in my 1.0 molar minus 2x here. So because I have squared divided by 1.0 molar minus 2x squared, I can take the square root of both sides. All right, so I'm going to take the square root of 24, which is equal to the square root of x squared divided by 1.0 molar minus 2x squared, okay? That is going to give me 4.9, which is equal to x divided by 1.0 molar minus 2x. So I go ahead and cross multiply here. That means I'm going to have 4.9 multiplied by 1.0 and 4.9 multiplied by 2x, okay? So that's going to give me 4.9 times 1 is just 4.9. minus 4.9 times 2, which is 9.8x. Okay, I'm going to add 9.8x to the other side so I can isolate x on its own. Once I go ahead and isolate x, remember there's a 1 in front of it here, I get 4.9 is equal to 10.8x. I'm going to divide by 10.8x so that I can again isolate x on its own. Now I have 4.9 molar divided by 10.8, and therefore my x value, which is going to be the solubility at AgBr, is 0.45 molar, folks. Deep breath. We have finally made it through our chemical Avenger journey, folks. Our chemical Avenger journey of all of this aqueous equilibria, from acid and bases to salt solutions to now solubility and complex ions. These last two chapters really complement one another, right? So now let's go ahead and get into our bonus video where we get to see the chemical Avengers in action, where they get to save equilibrium, folks.